schon aufmachen.
All right, I would like to welcome you at the second press conference at the EGU Assembly. The theme is Spacequakes, and first Rumi Nakamura, she's from the Space Research Institute from Austria. She will explain something general, and then Evgeny, Panov and Wolfgang Baumjohann are also from Austria, and Karl-Heinz Glassmeier is from das Institut für Geophysik und Extraterrestrische Physik from Germany. So I would like Rumi Nakamura to start.
Thank you very much for the introduction. Good afternoon. As I said, my name is Rumi Nakamura from Austria, Institut für Weltraumforschung der Österreichischen Akademie der Wissenschaften. And we are three of us with Professor Karl-Heinz Glassmeier from Germany. And we would like to talk about the spacequakes. And I will talk first the background, but I want to show, I will talk about in general what we are into, what the ultimate source of the spacequakes. Evgeny Panov will talk about THEMIS new findings, and Professor Glassmeier will talk about spacequakes itself. He will explain more what is the thinking behind, and then Professor Wolfgang Baumjohann will talk about impact on Earth, and I take question and answers. As you see, the ultimate energy for us in this living for us is the sun. And of course, you see the sun-Earth connection. You can see the sun erupting. And I think you might have seen the SDO, nice picture of the solar flares. But some of them come indeed toward the Earth. And then it has a strong plasma, energetic particles called plasma, which is the charged particles. And they're moving around 1 million kilometers per hour toward the Earth and jetting toward the Earth, as you see here in the cartoon. And as you see, when it comes close to the Earth, it takes about 2-3 days to reach the closer region of the Earth, which is called the Earth's magnetosphere. Why we call this is because Earth has magnetic field, and it's a territory, so to speak, is the Earth's magnetosphere. And what we are talking about is this region, what is happening there, and that's what we had the new observation, and also the ultimate goal is to understand the sun-Earth interaction. And as you see in the day side or the side of the sun, it hits the plasma, and the plasma tried to penetrate toward the Earth. However, the magnetic field protects us, namely, to prevent it toward the coming directly to the Earth. However, actually there are several processes. I said everything can protect us. However, small penetration of the solar wind plasma can actually happen, and this moving feature shows us. Actually, it's a very complicated process, but at the day side or where the sun side, these are the magnetic field lines which jetting with the solar wind plasma. They have this kind of connection and reconnect. These are the field line coming from the sun. This is the Earth side, and they reconnect, and they are transported toward the backside. And so there's a backside. There's another region where you have this kind of penetration. They reconnect, the field line reconnect, and there is a J cross B force happening, and they are accelerating actually the plasma. So I said 10% of the solar wind energy, although its a percentage is small, they actually penetrate. It's not only that they protect us, but it penetrates backside from the tail, from the night side. And here it happens that it gets accelerated because of this process, which is called magnetic reconnection. And this jet is actually jetting towards this, from the backside toward the Earth. And so again, here, the Earth's magnetosphere is therefore endangered by this plasma, which is jetting. And so a night side reconnection jet actually can hit toward the Earth. But this is not happening, and this is actually our theme, which I will show you today, or we are showing today. And actually, As you show here, the reconnection happens. This is more simplified cartoons. What happens when the plasma jets reach toward the Earth, like this one? And this was actually not unclear. As I said, it can reaches, but I don't know how does it comes from. You see sometimes aurora in the night side, something's going on. But until now, there was not so good observation in this area. However, there was the Themis, which you might heard somewhere else. But this is 2000. This started in 2007 in February. It's already launched and had very nice results in a general understanding of this area. However, we have particular spacecraft configuration. And you can see here, these are the old spacecraft. These 5 spacecraft are closely located where exactly these jets hits to the Earth. And they have 5 probes. There are 5 probes, 5 spacecraft with identical instrument measuring the plasma and electromagnetic fields. And so with this specific configuration, it realized for the first time an ideal configuration to study this near-Earth consequence of these plasma jets hitting from the tail side. And so I will show you, Dr. Evgeny Panov will show you now the real observation, what he found from the Themis 5 spacecraft study. So please.
So these 2 images, white images, they show the very first observations of what happens to that hostile flows which are going from the down tail to the Earth's magnetosphere, down to the magnetic field lines of the Earth's magnetosphere. And you can see here the equatorial plane observation. And this is the direction which is shown here in this figure by the red line. And this direction is along the green line. So, and the 5 spacecraft, which are these color dots, they are located somewhere here, as was shown in the previous view graph. And from the observations, you can see that the flow, when it's coming towards the Earth, it starts to be diverted duskward and downward in that region. And then, after some time, when the flow rebuffed down tailward, one can also see that it is diverted again duskward and downward, but the diversion pattern is opposite to what we saw in the first picture. And we came up, we took these observations and we came up with the idea how what's going on here. And if we imagine a jet coming from the down tail towards the monopolar field line of the Earth's magnetosphere, suddenly it hits it and the field line is getting indented, and in the equatorial plane we see this diversion pattern here. Then this indentation in the blue line, the dipolar field line, also starts to push the flow down tailward, and it is shown in the third sketch here. And you start to see this sort of flow behavior. And the disadvantage of the spacecraft observation is that we have only 5 spacecraft, and which are located in only 5 points of space, and this is a very limited observations, and we don't know really what is going on in the other points of space. But we, in principle, can model that situation to some extent and to get some supportive or facts from the computer simulations. And here, this movie shows the very procedure of the flow which is coming from the down tailward region, hitting the dipolar field lines of the Earth's magnetosphere, and is rebuffed tailward. And in this part of the figure, you see the first snapshot, which shows the earthward propagation of the flow. diversion pattern, duskward and downward, like it is shown on this sketch. And the right-hand side of the figure shows the rebuffed flow with the diversion pattern like here. So the idea is that what you observe is not only this one rebuffing, but also you see more oscillations, and what you see in this oscillation is a damping. So the first earthward flow was of the order of 300 kilometers per second, then it gets like 150 kilometers per second, then it goes down to only 100 kilometers per second, and so on. And that could be compared to a situation when somebody is throwing a ball or a log on the water surface, and the ball starts to oscillate, bobbing up and down, and with time the oscillation stops.
Okay, so as you see, this you can see this oscillation in the magnetosphere observed for the first time, so the THEMIS. But now Professor Karl-Heinz Glassmeier will talk about more extended view of this quaking stuff.
Well, we call this whole process Spacequake, and of course there is some analogy with what is understood as an earthquake. An earthquake is normally a very disastrous event, but so you can ask yourself what is happening to the ground if you have such a spacequake happening on the night side of the Earth. The first message is it's not that disastrous than an earthquake, but it's very beautiful. It's auroral activity which is also triggered by this activity. So the spacequake, has an optical signature which you can see here in the upper right. The optical aurora is oscillating back and forth in intensity, and that is a direct consequence of this spacequake. But there is also another possibility to detect this spacequake, and that is by watching the Earth's magnetic field. The easiest way to detect the Earth's magnetic field is just to take a compass. And if your compass is sensitive enough, then you can see that the compass needle is moving back and forth. And if you would observe such a spacequake while you are looking at your compass, and if your compass is really good, and normally with scientific compasses, electronic compasses, you can really detect that, you would see that the needle is going up and down and then is damped out until it is at rest again. This is what you see in the middle signature here. And if you compare the ground magnetic signature with the observations of the plasma jet bouncing back and forth on the night side, you see the nice correspondence. And this is the reason why we like to call this a spacequake. You might be interested in energies also. A typical spacequake, if you just look on how much energy is involved, compares to an earthquake of magnitude 6.2, 6.3. This is about a comparative number what we have here. And here you can see again the analogy in terms of the signals. We can see on the left side you see again a ground magnetogram, an isolated one, and further down you see magnetograms from many stations at the ground. It's a very busy picture from a very strong spacequake we observed. It's a so-called Bastille Day happening on July 14th, 2000. And on the right side you see corresponding signatures from seismic activity. The seismogram also shows a very nice dam-type curve corresponding to what we see in space or at the ground. And what you also see on the lower right part is just a series of magnetograms which have been recorded during the recent China earthquake on April 14. So there is an analogy between both events, but earthquakes are very disastrous and spacequakes are not that disastrous.
As you see, they look indeed so, in a sense, similar time scale, and this is just remarkable. So, however, of course, as Professor Karl-Heinz Glassmeier said, it's very disastrous. And what happens in the disastrous or active space weather, that storm event, will be now introduced by Professor Dr. Baumjohann.
Yeah, I think the spacequake that Karl-Heinz showed, the one that kind of was the same as this kind of plasma jet that hit the inner magnetosphere and then was rebuffed and bounced several times. That was kind of a very small spacequake. That was like the kind of normal earthquake you would probably encounter when you go to Japan. You wake up in the morning or in the night in a hotel room. You don't know whether you had too much beer maybe the previous evening because it's a bit shaking, and the next day your Japanese host tell you, okay, there was a small earthquake, and that happens ever so often, nothing serious. But sometimes you get these big earthquakes, spacequakes, a Bastille Day, space weather event, and then you see that the kind of turning of your magnetic compass needle or the aurora, they have two different causes. One is the aurora, of course, is caused by energetic particles coming down into the atmosphere, like in the neon light you have in your rooms nowadays, or you will have in all your rooms pretty soon if the European Union goes on like that. And they, of course, endanger also life in space and even life in the upper reaches. So if you fly, for example, to Tokyo, or if you fly to Los Angeles from here, you fly at rather northern latitudes, and you may see the aurora, and as a passenger you may see, okay, that's fine, but as a pilot or somebody from the cabin staff, where you have to fly that several times, you amount a couple of sieverts per flight, and at some stage you may not find that so nice anymore. Or if you have the magnetic compass needle deflection, then you know that can only happen when there are currents flowing in the ionosphere. If there are currents flowing in the ionosphere, there will be induction currents in any kind of big magnetic metal line, may it be a power line, may it be a pipeline for oil that's up in the northern parts. So people living in Scandinavia, people living in Canada also, are quite interested, pipelines, power lines, to see that. People having spacecraft up there are quite interested to know when these big events will happen. And while people are not really affected by that, and the kind of disaster is not so high in terms of maybe billions of dollars destroyed, but millions of dollars might be destroyed, and you want to know what's really happening there. And so the spacequakes needs to be studied, or the effect really what's happening there is also important to really understand how the space weather works. And that's why we need to understand them better, to really see how does energy that's in the outer magnetosphere gets into the inner magnetosphere. And that's why the process we are detecting now is so important also for the whole understanding of the energy flow in the magnetosphere.
Thank you. So as a summary, you can see again, as I said, the hostile solar wind coming toward the Earth, and indeed this Earth's magnetic field shields quite well. However, if you consider the whole energy process, we don't have to forget that this energy comes at least 10% coming from the backside, and particularly important is that there will be accelerated again. So that's why we have this fast flow, high-speed plasma jet coming from the night side toward the Earth. And then, however, because what we saw, this flow will be rebuffed because Earth has magnetic field after all again. And so in the backside also, Earth is protecting us from this attacking from the plasma. So in the magnetosphere where the field is large, magnetic field is larger, they rebuff this fast plasma jet backwards, as you see here, and doing this back and forth, quaking it, and thereby causing the spacequakes. And these spacequakes happening in the magnetosphere, again, you can see as an aurora. Nice event is just the aurora. Big event, you got more effect in the Earth of life. But as you see, in the whole process starts from the source region, where it's in the magnetosphere, and again coming from the sun. And so it's very important to have this observation, understanding the source, what is happening, and the interaction with the ionosphere. So that's, I would like to close our understanding of the presentation, and I will take questions. And as you see, you can have different language. You can have English, German, or Japanese, or Russian. And also, if you like to see more in detail, we have also several presentations during these EGU conferences and also publication. So, thank you. So.
Well, the magnitude, of course, is a term which comes from seismic events, and if you turn the magnitude into energy release and compare that, we have a view graph. Yes.
Actually,
for very small ones, the magnitude is 5.5. For most of the observed spacequakes, the magnitude is 6.1, and if we have a very strong storm, it's about 6.8, which would correspond to the recent China earthquake. So that is about the energy which is released in case of very strong spacequakes is 10 to the 15 joule, which is not small.
But there's of course one difference. Space is larger than the region on Earth that's affected by an earthquake. Of course, you saw the disasters that happened, like at the recent China earthquake or the Peruvian earthquakes. There are always this kind of 6.9, 7.1 or whatever, and there was really a disaster. But it happened over a rather limited area, a couple of square kilometers, tens of 100 square kilometers, while we are talking about, you see the width of the plasma jet. It's 6,000 kilometers, that's a radius of the Earth, or 30,000 kilometers. The Earth fits several times into this plasma jet. So the space is large, so the 10 to the 15th joule is distributed over a very large area. So the energy density is much smaller. The total energy is the same, but the energy density is smaller. That's our advantage. If it would be the same energy density, we probably should dig into the ground. I'm quite
a typical hypocenter of an earthquake is at a couple of tens of kilometers. So that's the distance we have from the surface to the source region. In case of these spacequakes, at the Earth's surface, we are 10,000s of kilometers away. So the direct impact is small. But if you would have a spacecraft being located close to the spacequake origin, then it could have a disastrous event. And because we are more and more populating space by technology, space station, communication satellites, I think it's very important for them and for them being able to operate, to understand what these processes, what is causing these processes and how we can predict them. And that really requires very detailed knowledge about these physical processes, and CMIS is a brilliant tool to understand in detail.
More questions?
Are auroras triggered by that storms? Auroras are triggered by storm
by storm activity, yes. By spacequakes and what we also substorms, by spacequakes, yes.
Spacequakes triggering
aurora.
Yeah.
Okay. The activity on the night side of the Earth in the magnetosphere triggers the aurora.
So for this particular case, you saw this very, there was some viewers which showing this localized aurora. Sometimes, however, if the big stop, this is a small laser, one plasma jet, small event. However, if you have this storm, a big event, you have really big event of larger aurora.
Actually, each of these plasma jets was triggering aurora. I think that's known, but this is now knowing a bit better how the aurora is really triggered.
About how long does it take for the reconnection and aurora to occur on the night side once you have the hit on the day side?
Oh, the velocities are a couple of 100 kilometers per second. So if the whole process occurs at, say, 15 Earth radii, which is 100,000 kilometers, it's a minute, 2 minutes about. So it's a very fast arrival time.
But I think not from the day side. I think.
On the night
Oh,
side.
yeah,
Yeah.
from night side.
Yeah,
On the night
Right, I
side.
mean,
But
once
before-
once the solar wind hits the day side,
Oh yeah, then it's
for
yeah.
reconnection to take place, and you see the.
Oh, that
aurora.
that
That's
takes a
it.
longer time.
That,
Yeah.
that takes
That
like
takes a longer time.
between 15 minutes and half an hour or so. It depends on the solar wind speed, and so 15 minutes, half an hour,
Or,
roughly.
or longer, yeah.
And what is the amplitude of this oscillation? The amplitude
At the ground.
of the field line?
Well, in space, the amplitude may reach like 30,000 kilometers, so it's a rather huge oscillation.
You mean magnetic field?
The magnetic field line moving back and forth.
Back and
Yes.
forth.
From 6,000 to 30,000 kilometers.
Yes.
it bounces.
Yeah,
So the
Well,
moving back, you mean this motion, or are you saying, yeah,
Yes.
Yes.
this
He
motion
He means that
itself.
motion.
So 5 times the movement. It changes the position 5.
That is a period. It's you have the field line.
Yeah.
View the field line as a ribbon, and it's moved out and moving in and moving out, and the amplitude is becoming smaller and smaller.
That's what I mean.
And that's a
Yes.
damp type oscillation. And the extension, the excursion of the field line, that's several thousand kilometers.
Yeah.
From so minimum 6,000 to maximum 30,000. It
Yeah,
moves.
yeah,
this is-
approximately, and it takes for a single period like 100 seconds. So
Okay.
one minute. During 1 minute, you have the full oscillation.
All right. Okay. Thanks.
More questions? All right,
Okay.
then I'll thank you very much.
Please, thank you.
Thank you very much.
Thank
Thank you.